So, last time we talked about polar coordinates and how they work, and the fun part of polar coordinates is some of the interesting graphs you can get from graphing polar coordinate equations. You're used to rectangular coordinates, x and y, where y is a function of x. So you plug in your independent variable x, you get your corresponding dependent variable y, and that gives you a point on the plane. And so the graph would be as you go along the x-axis and get all different x coordinates, the y coordinates that go with them represent the height above the x-axis that you are above that particular x coordinate. So as x gets bigger, you're going along from left to right, and your graph is going up or down depending on as y gets bigger or smaller. With polar coordinate equations, typically they're arranged so that r is some function of theta. So you're thinking of theta as the independent variable and r as depending on theta. And here, as you go along and try different values of theta, you're not going across from left to right, you're going around in a circle from 0 all the way around to 2 pi. Or 0 to 360 degrees if you're in degrees, but most often we work in radians when we're doing this. And then as we go around, the r coordinate tells you how far out you are away from the pole. So as we go around from 0 to 2 pi, we're going further out or closer into the pole as r, which is your function of theta, gets bigger or smaller. So let's start with the example equation r equals 1 minus the cosine of theta. Here I've got a table showing various values of theta from 0 all the way around to 2 pi, and then what you get when you plug in those thetas to get the corresponding value of r. So like if you plug in 0, the cosine of 0 is 1, and 1 minus 1 is 0. If you plug in pi over 6, the cosine of pi over 6 is the square root of 3 over 2, and 1 minus that is approximately 0.13. The cosine of pi over 3 is 1/2, so 1 minus 1/2 is 1/2, or 0.5. The cosine of pi over 2 is 0, and 1 minus 0 is 1. The cosine of 2 pi over 3 is negative 1/2, and 1 minus negative 1/2 is 1.5, and so on, all the way around. And notice that because cosine always gives you a number between 1 and negative 1, the values we get for r are all between 1 minus 1 and 1 minus negative 1. That is, they're between 0 and 2. Now look at what happens when we plot these points. Here's the point 0, 0. Here's the point pi over 6, 0.13. Here's the point pi over 3, 0.5. When you're at an angle of pi over 3 and a distance of 0.5 or 1/2 a unit away from the pole. Here's the point where theta is pi over 2 and y is 1. When theta is 2 pi over 3 and y is, or r, sorry, is 1.5. When theta is pi, r is 2, so that gets you out here. And as we go around, these are all the points that we pass through. And then filling in all the points in between, here's what the curve looks like. This curve is the graph in polar coordinates of the equation r equals 1 minus cosine of theta. And this is an example of what's called a cardioid. And it's called that because it is heart-shaped. Cardioid is like cardiac, means heart. Now let's see how we could do this on like a graphing calculator or something like that to handle all the details for us. I've got my graphing calculator here. I'm going to push the mode button. I'm going to make sure I am in radians mode. because we are talking about going around from 0 to 2 pi, and that's radians. And I've had times when I've tried to do polar coordinate graphs on a calculator and it hasn't been working, and it's turned out to be because it was in degree mode. So we want to be in radians mode, and now go down a line and go over and select POL for polar, so that we are in polar coordinate mode. And now that we're in polar coordinate mode, if you hit this button up here, the y equals button, it's not going to be y's, it's going to be r's. It's going to be all set up to accept an equation in this form where r is some function of theta. So I'm going to go ahead and key that in, 1 minus cosine of, and when I hit this button here with the x and other symbols on it, including a theta, here it's going to give me the theta. I'm going to close the parentheses. Now let's see what happens if I go ahead and hit the graph button. Okay, that did graph correctly, but it's kind of small. We can't see it real well. So let's change the window settings. I'm going to hit the window button. Right now, the thetas are going from 0 to 6.28 something, which is 2 pi. So that is what we want for this particular graph, to go all the way around from 0 to 2 pi. Sometimes you will have to adjust this. Sometimes to get the full graph, you'll have to go around more than 0 to 2 pi. Here's the step value. We won't adjust this, but you can if you want. But I do want to adjust the x and y scales. Right now, x is showing from -10 to 10. And let's zoom in and just show the x's from -3 to 3, and also the y's from -3 to 3. And now if we graph it, it's zoomed in a lot. It's just showing the graph from -3 to 3 in the x and y directions. And it is a little bit lopsided because the screen on the calculator is wider than it is tall. It's not as circular as this, but other than that, it looks pretty good. So that's how you can use a graphing calculator to get graphs of polar coordinates. You can also use the Desmos graphing calculator, either the version that's online that you can use in a web browser or the app that you can get for your phone, and that's nice and easy to use. So before I do anything else, I'm going to hit the little wrench and select a polar coordinate grid. We don't absolutely have to do that, but it helps us to keep track of where we are when we're in polar coordinates. And now I'm going to type in r equals 1 minus the cosine of, and I'm just going to spell out the word theta, and it's going to put it in for me. I can also pick it off of the menus. And it's automatically gone in and said it's showing thetas from 0 to 2 pi. Usually it does a pretty good job of figuring out what the good range is for theta. And there's our graph. Now let me do something with this. Let me surround it with parentheses and stick a number a in front of it as a multiplier, so that r equals a times 1 minus the cosine of theta. And right now, this is where a is just 1, so it's still just 1 times what we had before. But what if I change that number? So instead of 1 times 1 minus cosine of theta, it is, say, 2 times that. Do you see what that does to the graph? It makes it larger. It blows it up because all the points are now twice as far away from the pole as they used to be. And so where we used to go out to just 1, now we're going out to 2. Where we used to go out to a distance of 2, now we're going out to 4. And so the whole thing just gets enlarged. If a is 3, it gets even bigger. So when you have a polar coordinate equation and you take the whole function of theta and multiply it by some number, that just scales the graph to make it that many times as large as it was originally. So this can be fun to play around with. And I'll say more about that in part 2. So I'm going to end this part of the video right now and come back in part 2, and we'll look at some more interesting polar graphs.